So if you're watching this video, you probably use the Python package Pandas, which is extremely powerful for working with data sets of various size. In this video, we're going to be talking about efficient memory use in Pandas. There are many reasons to make your Pandas data frames memory efficient. It can speed up the process that it takes to run code. It reduces the amount of memory that you're using so you can use that memory for other things. And depending on how you write your data to disk or to a database, it can make it more efficient when you store it. Hi, my name is Rob. I make videos about coding in Python and machine learning. And in this video, we're going to talk about efficient memory use in Pandas. Please consider liking and subscribing if you enjoy. All right, let's get on to it. Okay, so here we are in a Jupyter notebook, and we are going to start out by importing the same things we do all the time in other videos. Import pandas as PD, import numpy as NP. And now we're gonna create our data. We're gonna start out by making some fictitious data. Let's just pretend this data is for a sports team, and we're gonna create a Pandas data frame to start. So we're going to start out with a column that will be the position of the players. Each row will just be a random value. We'll use numpy random choice to give a random value either left, middle, or right. And it's going to be of the size. Then we're going to add another column called age. This is going to be a random integer between 1 and 50. We'll make the team. So the different teams could be red, blue, yellow, or green. We'll make a value for if they win or not. So that's going to be NP random choice, yes or no. And lastly, let's make another column called prob for maybe the probability. This is going to be a random uniform value between 0 and 1. Great. So if we look at the head of this data set, we can see that we have float integer as prob, yes or no, the age, position, all of this looks good. And the shape should be 1,000 rows. Let's just quickly wrap this in a function, and this will return the data frame. Now we're going to want to test this on a fairly large example data set. So let's create our fake data set that's 1 million rows now. And if I create this and do df.info, we're going to see some information about the data set. We could see that in memory, this data set is taking 38.1 megabytes of RAM. Now imagine as this data gets bigger and bigger, let's say it's 3.8 gigabytes or 3.8 terabytes, the size that we have it in our data frame format is really going to matter. And not only that, we want to be working with our data set in a way that's as fast as possible. So let's show as an example some group by aggregation. So if we group by the team and the position, and then we take the rank of the age, we could add this as an age rank column. Similarly, let's do something for the probability rank. And I need to rename that team so it's correct. So after running this, we have new columns for the rank and age grouped by team and position, and the rank and probability grouped by team and position. Let's get an idea for how long this takes to run by running our time it. Now this will run several different loops of each line of code, and then tell us how long each of them take on average and the standard deviation. So you can see this first group by aggregation took 333 milliseconds. The next one took 430. So what it really comes down to is we're going to make our data frame efficient by the dtypes that we cast each column as. And right now it's not very efficient. And we're going to start by working with this position column. So if you remember, the position column can either be middle, left, or right. And right now it is just an object of type string. So each of these values are a string type. But a much more efficient way to store this is as a categorical type. So we're going to take it and take position, and we're going to cast it as type category and overwrite that column. Let's do this from a clean data set using our get dataset function. and run our info on it to see what the data set size is. So just by casting this data type as a category, we've reduced the size from 38 megabytes to 31 megabytes, and the data itself hasn't changed at all. Let's go ahead and do the same casting on our team, because that we know is a value that's a category type, even though it's as a string right now. Now keep in mind, casting as a category wouldn't work if you have every row being a unique value in this column and it truly is a string. But in this case, both of these we know to be category types, and we can get our data frame already down to 24.8 megabytes in size. All right, next we're going to deal with the age column. The age column is stored as a integer, and by default, Pandas will read in integer values as a int64 value. And 64 just basically stands for how much memory or how many bits per row is it going to use to store this value. And you can get away with changing this int64 to lower values depending on the range of your integer values. And just for an example, I'm going to show you int downcasting value range. So depending on what we downcast this to, we need to make sure that our values are between these ranges in order for us to not lose any data. And we know that our age value has a max value of 49 and a minimum value of 1. So that could fall within this negative 128 to 127 range. And we could actually downcast this as type int8 and not lose any information. And if we run df info on our data set now, we can see that it's even smaller, 18 megabytes as opposed to 24 with our casted categories. And we're going to do something very similar to the probability column. This is a type float64. And for floats, it's a little bit different because it really impacts the precision of how many decimal places that our data can store. So if we look here between the probability and I show it casted as a 16, it does change the values a little bit. So we're going to actually make this a float 32 to make sure that we have at least the same values here to 6 decimal places. And if we look at the size of the data frame now, we're down to 14.3 megabytes as opposed to before. So this is downcasting floats. So let's just take everything we've done so far and put it all together and call a function. Let's call this function set dtypes for the data frame. In this, we'll cast those two columns as categories like we did before. We'll cast the age as a int8, and we'll cast the probability as a float. Oh, and there's one more thing I forgot about to mention before, and that's going to be casting Bool types or true false columns. If you remember, we have this column called when, and the values in it are text fields, string values that say either yes or no. However, in this case, we can actually make this column the D type that uses the least amount of memory out of them all, and that's a bool. It's just a simple 0 or 1, true or false. And the way we can cast this is by taking this when string value, and we can map a dictionary onto this. So when the value is yes, it'll be true. And when the value is no, it'll be false. And you can see here that the D type of this column is now a bool. And to show the info size on this, it's down to 7 megabytes from what it was before. So a quarter of the size of what it was before we did all this memory reduction. Now to run the same test we did before with our downcasting and specific D type selection, we're just going to run this cell before on a data set. So first we're going to run it on our original data set. This is doing all the group by and ranking across the whole data set, which is 1,000,000 rows. And then we're going to do the exact same thing, but after setting our D types by running this set D types function. So we can see that pretty much across the board, we've made things run faster. And this is not necessarily even linear. So the even larger that you make the data, the bigger this gap might be. And it really depends on your data set. So let's run the same test with an absolutely huge data frame. So we're going to up the ante with the size by just running this as 10 times as large as we've been testing with so far. Okay, it's finally done, and you can see that these took a while to run, each different timing, and we're going to do the exact same thing after casting the dtypes. Pull the same data set and then cast the dtypes and run these exact same functions and see how fast it goes. Okay, and that's done running, and you can see pretty much across the board that we've saved time as well as memory by casting these dtypes on the larger data set. Now, in addition to the reduced memory use and the time saving for computation, depending on how you save the data to disk, you could save disk space by casting these dtypes. In a future video, I intend to talk about saving data frames to disk using Parquet format, and those would be much smaller if you cast your dtypes correctly. Thanks for taking the time to watch this video. I hope you enjoyed it. Remember to like and subscribe, and I'll see you all in the next one.